Oh yes, it is. Here we are, chapter 4, lesson number 11. We have made it to the end of the chapter on differential equations. So, this is looking at the amended particular integral. You'll notice in the other videos when it comes to choosing the particular integral, I say try this. And the reason I say try is because sometimes your particular integral does not work and we have to change it. This has to be done when the form of the particular integral already appears in the complementary function, which you will have found before that. The way we change the particular integral is to just multiply it by x. If that already appears in the complementary function, you multiply by x again. Let me show you with this example. So, examples 1 to 13 are in the previous lessons, so we're starting here with example 14. Find the general solution of the second order differential equation d2y by dx squared minus y equals 2e to the power of x. So, Valley, what would you do first of all if you were solving this? Perfect, you would come up with the complementary function. And to get the complementary function, you think of your auxiliary equation. So you take the coefficients of d2y by dx squared, dy by dx and y. And we have 1 d2y by dx squared, so that'll be 1k squared. We've got 0 dy by dx, and we've got minus 1y, which will be minus 1 in the auxiliary equation. If we were solving that, we would factorize, so we get k plus 1, k minus 1, giving us two values of k of negative 1 and 1. And that means the roots are real and distinct. If the roots are real and distinct, we've got 1 and minus 1. Well, what does that mean? Well, that means then the roots are real and distinct, so we've got k equals p, k equals q, so 1 minus 1, so our complementary function will look like that. ae to the power of negative x plus be to the power of x. So after that, what do we then do? Well, next we want to look at the particular integral. However, I'm going to show you this one which will not work, so don't bother copying this unless you're wanting an example of why it won't. So a particular integral, normally what you would do is if we flip back, we can see that the right hand side equals 2e to the power of x. So for the particular integral, we would choose something e to the power of x. So let's say we tried pe to the power of x. We know after that we would differentiate. We would come up with dy by dx, and if you differentiate pe to the power of x, it stays as pe to the power of x. We would differentiate again to get the second derivative, and that would give us, again, pe to the power of x. What we then do is, if we look at the original equation, we've got d2y by dx squared minus y, so we can replace the d2y by dx squared and the y into that original equation. If we do that, d2y by dx squared is pe to the power of x, and we're taking away y, which is pe to the power of x, and that equals that right-hand side. However, if you simplify this left-hand side, you would have pe to the power of x take away pe to the power of x, which is 0 pe to the power of x, or in other words, it could just be 0. But if you look at the coefficients of e to the power of x, well, here the coefficient is 0p, and here the coefficient is 2, which gives you 0p equals 2. There is no number that you can multiply 0 by to get 2. It makes no sense. Confusing. Yes. Really, this doesn't work because if you look at that particular integral, something e to the power of x, well, we already have that in the complementary function. We have something e to the power of x. The b, the q, it doesn't matter. That's just going to be a constant. We have something e to the power of x. So it doesn't work. So we have to amend the particular integral. This bit here is what you should copy. So if we copy this then, for the particular integral, again, we can't choose pe to the power of x because the complementary function already has a something e to the power of x. So let's multiply the particular integral by x, so we'd have px e to the power of x. So, once again, you have to get dy by dx and d2y by dx squared. So, getting dy by dx, we differentiate pe to the power of x, and to differentiate we use the product rule. You got it. So the product rule, u dash v plus uv dash. let's have u and v. So u, let's let that equal px, and v, let's say that's e to the power of x. Well, e to the power of x, dead easy, stays as e to the power of x. Px, oof, dead easy as well, it just goes to p, which means then dy by dx would equal u dash v plus uv dash. So you get p e to the power of x plus px e to the power of x, and I suppose you could take out a common factor there of p e to the power of x, giving you p e to the power of x bracket 1 plus x. We need to get the second derivative as well, so for the second derivative, again we have to differentiate. If we differentiate p e to the power of x times 1 plus x, what would you use? Product rule! You got it! So the product rule, u and v again, u is p e to the power of x, v is 1 plus x. U dash, differentiate p e to the power of x, it stays the same. Differentiate 1 plus x, well, that's 1 plus 1x, so differentiate that, it goes to 1. d2y by dx squared would equal u dash v plus uv dash. So p e to the power of x times 1 plus x plus p e to the power of x times 1. Multiply out the brackets there to have p e to the power of x plus x p e to the power of x plus p e to the power of x. Meaning then, well, this first and the last term, you can add them together, so you've got 2p to the power of x plus x p to the power of x. And again, you could take out a common factor of p to the power of x, in brackets, x plus 2. It means then that we have y, we've got dy by dx, and we've got d2y by dx squared, so we can sub them into that original equation right at the start. So we're replacing d2y by dx squared with this, and we're replacing y with this. If we do that, then we will have p to the power of x times 2 plus x take away px e to the power of x, and that would equal this right hand side. Multiply the brackets there, I have 2p to the power of x plus px e to the power of x, take away px e to the power of x. Well, if you look at that, both this term and this term will cancel, leaving you with 2p to the power of x equals 2e to the power of x. We need to find the value of p, and the way we do that is we look at the coefficients. Look at the coefficients of e to the power of x. They have to be the same on the left and the right because both sides are equal. So you can say then over here you've got 2p e to the power of x, and here you've got 2 e to the power of x. So if we equate the coefficients, we know then that 2p must equal 2, meaning that p equals 1. Therefore, the particular integral, we had px e to the power of x. Because we have found that p is equal to 1, we can replace that, so that becomes 1x e to the power of x. Once again, how do you get the general solution? Anybody remember? Perfect. You get the complementary function and you add the particular integral. So here your general solution will be the complementary function was ae to the power of negative x plus be to the power of x, and we're adding on that particular integral. And that there, kaboom, is your answer. Example 15, find the general solution of the second order differential equation d2y by dx squared plus y equals 2x, 2 cos x. So, first of all, again, we need the complementary function. So think about the auxiliary equation. So for the auxiliary equation, take the coefficients of d2y by dx squared, dy by dx and y. So we've got 1, we'd have 0, and we'd have 1. So 1k squared plus 0k plus 1 would equal 0. Solving that, well, if we subtract 1 from both sides, we know that k squared would equal negative 1. If we take the square root, well, k would equal plus or minus the square root of negative 1. And the square root of negative 1 we call I. Perfect. So we're going to have 0, real parts, plus or minus 1i. So you're bringing in the real and imaginary numbers. Here you can say then that we have complex conjugates as the roots. What does that mean then? Well, again, think back to this wee table. Woo! Wee table! You can say that y equals e to the power of the real part times x. So it'll be e to the power of 0 times x. Bracket a sine imaginary part times x. Here, the imaginary part is just going to be 1, so it'll be 1x plus b cos 1x, and you could simplify that. Next, what you want to do is you want to look for the particular integral. And a lot of the time what you would do is you would look here and you think, for this then I've got 2 cos x. So for the particular integral, I would choose something like p cos x plus q sine x. But if you look at it, the sine x and the cos x terms are already here in the complementary function. So a lot of the time you would choose p sine x and q cos x, but these terms already appear. We already have a something sine x. P sine x means something sine x. Q cos x as well means something cos x. We already have a something cos x, a constant times cos x. So because they already appear, it won't work out. Again, we'll get down to something like 0 equals some number, which makes no sense. So we have to amend the particular integral. And we do that by multiplying what we would have as a particular integral by x. So for the particular integral in this case, we are going to try p sine x plus q cos x, but we're multiplying that by x. We know after we get the particular integral, we have to differentiate that. And we differentiate it again to get d2y by dx squared. So let's do that. Differentiating this particular integral, how would you do that? Perfect. Once again, you want to use a product rule because it's x times something in terms of x. So let u equal x, u dash therefore will be 1. V is going to be p sine x plus q cos x. And if you differentiate that, you will end up with p cos x minus q sine x. dy by dx therefore is u dash v plus uv dash, which gives you p sine x plus q cos x plus x times p cos x minus q sine x. So we have dy by dx, but we want to also get d2y by dx squared, so we differentiate once again. We can differentiate these two terms easily enough, but here you've got something in terms of x times something in terms of x. So you use the product rule. So let u equal x once again. U dash will equal 1. V is going to equal p cos x minus q sine x. And if you differentiate those terms, you get negative p sine x minus q cos x. d2y by dx squared therefore will become, well, if you differentiate p sine x, you get p cos x. Differentiate positive q cos x, you would get negative q sine x. And then you're bringing in u dash v plus u v dash for differentiating this part here. That is what you will end up with. Multiply out the brackets, and that is what you will get. But you can then simplify those terms, and that will give you 2p cos x, because we have a p cos x plus a p cos x, and we've got a minus q sine x, take away another q sine x, so minus 2q sine x, and these terms would stay as they are. What we now do, because we have d2y by dx squared, dy by dx and y, we can sub them into the original equation which we started with in the question. d2y by dx squared plus y equals 2 cos x. Doing that, replacing d2y by dx squared with all of this will give us that. And replace y with x brackets, all of it in the brackets, will give us that, and it equals 2 cos x. Let's get rid of the brackets, multiply them out. That is what we end up with. And if you look at this, well, it simplifies down to something that's nice and easy. You get 2p cos x minus 2q sine x. You have a minus px sine x and you have a plus px sine x. So these two terms will cancel out. So that term cancels with that term. And we have a minus qx cos x plus qx cos x. So that term will also cancel. So that is what we get down to. We need to find these values of p and q. How could we go about doing that, Fiona? What do you think we would do? Equate the coefficients. Perfect. From there, you equate the coefficients. So we've got down to 2p cos x minus 2q sine x equals 2 cos x. Look at the coefficients, first of all, of cos x. So we've got cos x here and here. So take the coefficients of cos x. Well, on the left-hand side, we've got 2p cos x's. So we can say that 2p equals, and on the right-hand side, we've got 2 cos x's. So we know that the 2p must equal 2. Divide both sides by 2, and p equals 1. We then need to look at the coefficients of sine x. So number of sine x is here. Well, it's minus 2q sine x. And for sine x is over here, well, you can see there are none. It's 0 sine x. So if you equate those coefficients, you can say that this negative 2q must equal 0. And if negative 2q equals 0, well, it's negative 2 times what is 0? Well, that's just 0. Because we have found the values of p and q, we can say then that the particular integral, we had x p sine x plus q cos x. We have just found these values of p and q, which means that the particular integral becomes x times 1 sine x, which is just x sine x, and that there, because we're multiplying it by 0, will disappear. Poof. The general solution then is the complementary function plus the particular integral. The complementary function was that, and the particular integral is x sine x. So therefore, we have that as the general solution. Yo! Example 16, find the particular solution of the second order differential equation d2y by dx squared minus 6 dy by dx plus 9y equals 4e to the power of 3x. But this time we are told that when x equals 0, y is 1 and dy by dx is negative 1. Woo! So the first thing that we do to get the particular solution, well, we have to go through and get the general solution first of all, and we do that by coming up with the complementary function. So think of the auxiliary equation, take the coefficients of d2y by dx squared, dy by dx and y, and we would have 1k squared minus 6k plus 9 equals 0. We would solve that by factorizing. That will give us, brilliant, k take away 3, k take away 3, which means k equals 3, and that is a repeated root. Because we have a repeated root, woo, that means then we're going to have y equals ax plus b e to the power of px. So roots are real and equal. Because k is 3, we are going to come up with y equals ax plus b e to the power of 3x. So that there is the complementary function. What we do next is we look for the particular integral. So the particular integral, because this right hand side is something e to the power of 3x, a lot of the time you would go for pe to the power of 3x. However, if you look at the complementary function, well, imagine if you multiplied this out, we would have a something e to the power of 3x. So we cannot choose something e to the power of 3x, pe to the power of 3x as the particular integral. What we would then do is multiply by x. So we would have px e to the power of 3x. But if you look at this still again, if you multiplied this out, you'd have something x e to the power of 3x, which means px e to the power of 3x would also not work. Mamma mia! So what we've got to do again is multiply by x. So if you multiply by x, we would have px squared e to the power of 3x. If you didn't notice this and just went through with pe to the power of 3x, you'll find it doesn't work. If you multiplied by x and got px e to the power of 3x, again you'll find it doesn't work. It's absolutely fine to do that, it just wastes a little time. Look at the complementary function and just see if it already appears. If the particular integral that you're choosing already appears. So here something e to the power of 3x is already there, so that won't work. And if you have something x e to the power of 3x, we've got something x e to the power of 3x, that will not work. So multiply by x again. So therefore this will be the particular integral. You know from there, once you get the particular integral, you have to get dy by dx and d2y by dx squared. Because you've got something in terms of x times something in terms of x, you know you would have to use the product rule. So u is going to equal px squared, differentiate that, and you get 2px. v will equal e to the power of 3x, and if you differentiate that, you get 3e to the power of 3x. dy by dx, therefore, u dash v plus uv dash, u dash times v plus u times v dash will give us 2px e to the power of 3x plus 3px squared e to the power of 3x. So we have dy by dx. However, we need to differentiate that again to get d2y by dx squared. So if you look at it, we can differentiate this part here using the product rule. So let's do that. So if we take that part, well, we've got a 2px times e to the power of 3x. So let u equal 2px and v equal e to the power of 3x. Differentiate 2px, you get 2p. And differentiate e to the power of 3x, you get 3e to the power of 3x. So u dash v plus uv dash. But we're also adding on this part here. And for that, once again, we will have to use the product rule. So again, just go to the side. You can choose different letters if you want, but go to the side and let u equal, again, I'm going to choose 3px squared. And u dash, if you differentiate that, you will get 6px. V will equal e to the power of 3x. And if you differentiate that, you still have 3e to the power of 3x. Therefore, d2y by dx squared, well, you've got u dash v plus uv dash over here, giving you these first two terms, plus, and u dash v plus uv dash, giving you these next two terms. You'll notice that you've got a 6px e to the power of 3x twice, so if you add them together, you'd have a 12px e to the power of 3x just in the middle there. Because we now have y dy by dx and d2y by dx squared, we can sub them into the original equation, and that there was our original. So we're going to replace d2y by dx squared with all of this part here. We're going to replace dy by dx with this part here, and we're replacing y with this part just at the top. And doing that will give us this very ugly equation, 2p e to the power of 3x, blah, 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 blah. Take away 6 times the dy by dx, we sub that in, plus 9 times, and we subbed in y as well. Let's multiply out the brackets there. That is what we will end up with. However, that actually becomes something that's quite simple. If you start to cancel out different terms, well, you get down to 2p e to the power of 3x. What you'll notice is that you've got 9px squared e to the power of 3x, another 9px squared. If you add them together, you get 18, but you're taking the 18 away. And also, you've got this plus 12px, and you're taking away the 12px. So really, that is all you are left with, 2p e to the power of 3x. And that will equal the right-hand side. After that, you have to equate the coefficients in order to find out the value of p. So equate the coefficients of e to the power of 3x on the left and the right. So you'd have 2p equals 4. If 2p equals 4, then p would equal 2. So the particular integral, well, we had px squared e to the power of 3x. Because we know p is 2, that becomes 2x squared e to the power of 3x. Yeah. The general solution then, what are we going to have? Well, for the general solution, you know you're taking the complementary function, which was that, and you're adding on your particular integral. So that there is the general solution. However, stop right there. You're not actually done, because we were given this additional information. We were told that when x was 0, y was 1, and dy by dx was negative 1. So we can get the particular solution. In other words, find the values of a and b. So let's start off then. Take that general solution. Let's replace x with 0 and y with 1. If we do that, replace x with 0 and y with 1, we will have 1 equals a times 0 plus b times e to the power of 3 times 0 plus 2 times 0 squared e to the power of 3 times 0. Simplify all that, and it just gives you, well, a disappears, that just becomes 1, so it's 1 times b, which is b, and because you're multiplying all that by 0, it stays as 0, meaning that b is 1. Remember, you were also told that when x was 0, dy by dx was negative 1, so we're going to have to differentiate y. So differentiate that general solution. To differentiate, once again, you're thinking, look at this, you have something times something, and both somethings are functions in terms of x. So you're going to have to use the product rule. So u will equal ax plus b, and v will equal e to the power of 3x. U dash will equal a, and v dash will be 3e to the power of 3x. You're also looking at this part and you're thinking, again, you've got a function in terms of x times another function in terms of x. So to differentiate, u will equal 2x squared. U dash then will be 4x. V will equal e to the power of 3x. So again, we'd have 3e to the power of 3x. dy by dx then, if you differentiate over here, you'd have u dash v plus uv dash, which will give you that. A times e to the power of 3x plus 3e to the power of 3x times ax plus b, just writing in that form there, plus, and then again u dash v plus uv dash for these terms underlined in green. You know that when x is 0, dy by dx was negative 1, so you can replace dy by dx with negative 1, replace all the x's with 0, and that is what you would end up with. From there, that just becomes a times 1, which is a. You'd have a times 0, which is 0. That leaves you a b. It's b times 3 times that becomes 1, so it's 3b. Because you're times that by 0, it goes to 0. And because you're times this by 0 squared, in other words 0, that also goes to 0. So you get down to a plus 3b equals negative 1. But because you know b is 1, you can sub that in, meaning you can easily find that value of a. From there then, you know you can get the particular solution. All you're doing is you're going back to the general solution here. There's the general solution, but you're replacing the a and the b. A was negative 4, b was 1, so you're taking that general solution and you're subbing in those values of a and b, and that is your answer. Again, you may wish to write that so you're not starting with the negative. So that goes to 1 take away 4x, e to the power of 3x plus 2x squared, e to the power of 3x. And that there is your answer, and that there is the last example with second order differential equations. Have a go at these questions here. You're looking at amending the particular integral. Have a look at when you need to, why you do it. Practice these. Best of luck. Have fun. Woo! Bye. See ya.